Greetings, physicists. This video will be about solving electrical force problems. So we're looking at a couple of charged particles, and both of them have this charge, and they are this far apart on the x-axis. So let's draw that. They're both positive 10 nanocoulombs. I'm putting a box around them, but really we're going to approximate them as point charges. And they are this far apart, which is 2 centimeters. And then we put between them a 1 nanocoulomb charge, halfway between, 1.0 nanocoulombs. And if it doesn't say positive or negative, just assume it's positive. We want to know how much net force does that dude feel? And then we're going to change one of their charges and ask again. So, when you do these problems, these Coulomb's law problems, I'm going to make 2 recommendations. 1, don't do the math and plug in the positive and negative. You can, but that always screws me up when I try to put in positive, negative into my numbers in terms of direction. So that'll be the first one. The second one is don't put 10s into your calculator. That's not specific to this. I never like putting 10s into a calculator. Powers of 10. Unless you know your calculator really well and are comfortable with that. So the force between charged particles is equal to KQQ over R squared. We have an R. We have both Q's. And K is something that we can look up. Now I am going to have to change this to centimeters, and I'm going to have to change these from nanocoulombs to regular coulombs. And I'll show you that that's actually fairly simple. A centi of something is a 10 to the minus 2 of something, so I'm just going to move that decimal twice. So, well, you know what? I'm not going to move that decimal twice. I'm going to keep the powers of 10 in there because almost everything here is a power of 10. So K, if you didn't know, is 9 times 10 to the 9th, positive 9. The first Q is 10 nanocoulombs. That's 10 times, a nano is a 10 to the minus 9 of something. And I know that they are both that charge. Oh, excuse me. I was about to solve for the force between the 2 particles, right? But let's just make sure I know that I'm looking for the force on this guy. This guy is being pushed one way by this charge. So what's the force? Well, the force is based on his plus 10 nanocoulombs and his plus 1 nanocoulombs, okay? So let's put that 1 in there. 1 times 10 to the minus 9, because a nano is still a 10 to the minus 9. On bottom, that R was 2 centimeters, and a centi is a 10 to the minus 2 of something, which I am going to square. Now the reason I'm leaving all of that, watch this, is 10s are easy to deal with. I have 9 here and negative 9 here. That's going to go away. I have negative 9 on top, and squaring this, I'm going to have minus 4 on bottom. So if I get rid of all of that, I'm going to have 2 squared, which is 4, and I'm going to have 10 to the minus 4. And a 10 to the minus 9 subtract 10 to the minus 4, or divided by 10 to the minus 4 is going to be 10. So cancel those. I'll get a 10 to the minus 5 on top left over, times this 10. So that's actually going to drop to a minus 4. And I just got rid of all my 10s, and there's a 1 here. So what's left on top is really a 9, a 10 to the minus 4, divided by a 4. So 9 over 4 times 10 to the minus 4. I mean, you can do that. 9 over 4 is 2.25, right? So this is actually 2.25 times 10 to the minus 4 newtons. Not bad. Or 0.225 millinewtons. So not a big force. And the reason I did it that way is we were basically able to do that without a calculator, and we were able to do it fairly quickly. And a lot of times when students plug this stuff into their calculator, the 10s come out all wrong. Now, I need to make a point, though, that I would like to make a point if I could scroll, that number I just got, 2.25 10 to the minus 4, was the force, this force right here. the force that came from this particle and this particle. Don't forget, I'm also going to get a force of this guy pushing on this guy. Now the numbers will be exactly the same, it's just going to push in the other direction. So in the end, if I redraw this here, I have that force to the right, I have a similar force to the left. There will be no net force, and that should be kind of intuitive. You probably could have done that on your own by noticing that it was midway between two equally charged particles, so it should feel the exact same force from both. Oh, you know what? I just realized I made a mistake. Careful of that, because the distance between them is not 2, it's only 1, because he's halfway between. So I have to go back here. Notice that that will change the bottom. Where I had 2 squared, I'm actually going to have 1 squared, which is only 1. So, come on, eraser. Yes, is that fine? There we go, erase. Erase, erase, erase. So, if I do 9 divided by 1, yeah, it's just 9 times 10 to the minus 4. But that's from one side. The other side, I will get a 9 times 10 to the 4 in the opposite direction. So the net force, F net, on that particle from the electric charged particles is 0. Now it asks, what happens if I make one side negative? So I have the same setup. I have my 1 nanocoulomb particle here. I have my 10 nanocoulomb, oh, that's used to be lowercase, 10 nanocoulomb particle here, and on the other side I have a minus 10. So before, when they were both positive, and this is the before, it was one pushed, the other pushed, canceled out. But now if I look, this interaction between two positive particles is a push to this direction. This interaction between a positive and negative is a pull, so it's also going to go this direction. So now it does matter. So the magnitude has not changed, right? Just the sign. So when I plug all the numbers in, 9 times 10 to the 9th and 10 times 10 to the 9th and 1 times 10 to the 9th. Notice again, I'm not putting in the negative sign because again, that just screws me up. And then on the bottom, it will be 1, which is what I should have put the first time, times 10 to the minus 2, and I square it. I will get the exact same number, 9 times 10 to the minus 4. But now both 9 times 10 to the minus 4 newtons is going to the right. So I'm getting the same number in the same direction. So I just got to double this. So that's plus 9 times 10 to the minus 4. And 9 plus 9 is 18, so this is actually going to be a net force of 1.8 times 10 to the minus 3 newtons. Good stuff. So that's a sample Coulomb's law problem. Let's do another. 3 charged particles arranged as below, which I have to now arrange them. We have a negative charge here. It is minus 50 nanocoulombs. We have a positive charge here. It is plus 50 nanocoulombs. And we have a positive charge here, which is plus 30 nanocoulombs. We'll call this guy Q1, this guy Q2, this guy Q3. And we're going to make a dashed line here to pretend it goes straight up. The distance between here is 5 centimeters. The distance here is also 5 centimeters, so this is not drawn to scale, you can already tell. And the distance here is 5 centimeters. Okay. And what we're looking for is the net force on this charge, Q3, just based on this picture. Well, first I'm going to draw a free body diagram for him. He's going to be pushed this direction by this charge. He's going to be pulled this direction by this charge. So I'm really going to have to solve for both of those forces. So it looks like the net force will probably be somewhere between them, is my guess. But let's figure that out. I'm just going to solve for the magnitude right now, and we'll deal with directions later. So, the Coulomb's law, so what I'm looking at here is the guy is 30, and he is interacting with a 50 here. He's also interacting with a 50 here. And notice that there's a symmetry here, that he's 5 centimeters away in the x direction from both of those guys, and he's 5 centimeters away in the y direction from both of these guys. So these two forces should have the same magnitude because they are the same charge particle magnitude-wise, and they are the same distance away. So I can make one calculation and get the magnitude of both forces. So let's do that calculation. That calculation for the force should be the k value, which is 9 times 10 to the 9th, and each of their charges. And so the charge acting on him is a 50 nanocoulomb charge, or 50 times, 10 to the minus 9. His charge is a 30 nanocoulomb charge, or a 30 times 10 to the minus 9. The radius between them, and now here I have to do a little geometry. He is this far away, 5 and 5. So he's 5 square root of 2 away. Now I could multiply that out, but I'm not gonna. And is that meters? No, it was centimeters, right? Yeah. So that's 5 square root of 2 times 10 to the minus 2 meters. And I'm squaring that. Now when I square that, so if I come, let's see if I can scroll. If I square the bottom, 5 square root of 2, well, that's 25 times the square root of 2 squared, which is 2. So 25 times 2 is 50 on the bottom. 10 to the minus 2 squared is 10 to the minus 4. See how that goes? Up top, 9 times 10 to the 9th, 50 times 10 to the minus 9, and 30 10 to the minus 9. So look what that did by not having to multiply that out. I have a 50 that's going to cancel. I have a 10 to the minus 9 that's going to cancel. I have a 10 to the minus 9 here and a 10 to the minus 4 here, which is left over 10 to the minus 5. I can multiply by this 10. 30 is just 3 times 10. So if I just drop that down to a 3, I can drop this to a minus 4. 3 times 9 is 27 times 10 to the minus 4, or 2.7 times 10 to the minus 3. So again, this goes real fast if you don't plug it into your calculator. And that is a newtons. So because I did that, and I told you before that both forces are the same, when I redraw this, here we go. I have this force down is 2.7 times 10 to the minus 3, and this force here is 2.7 times 10 to the minus 3. So now let's make sure we know what direction they're pointing, because that's going to determine how I add them. I'm pretty sure they're 90 degrees to each other, but let's find out. The points were like this. That's 5. That's 5. That's 5. So the angle of this push is definitely a 45 degrees this way. And the angle of this push is definitely a 45 degrees this way. So they are 90 degrees to each other, which means that their vertical components should cancel out. So the only piece that goes forward, they both have a forward component, and that forward component should be equal. So if I can get this leg right here and double it for one of the forces, then that is my net force on that object. So I'm going to pick this guy here, right? We know that's a 45. We know this is the hypotenuse, so I can do a cosine. I can also do sine, because 45, 45, 90 is equivalent. So I can do 2.7 times 10 to the minus 3 times the cosine of 45. And I do need to be in degrees for this, in case you haven't swapped over yet. So, calculator up, 2.7 0.7 times 10 caret minus 3 times the cosine 45. All right, and I'm getting this number 1.9 times 10 to the minus 3 newtons. That's for one of the two forces, so I double that. So doubling that is 3.8 times 10 to the minus 3 newtons. So that's the net force that guy feels, and he feels it directly to the left. Now, of course, as soon as he starts to move, those angles will change, and so his trajectory will change. So this is just the force right at that moment. Okay, here we go. We've got some bees flying through the air. They're rubbing up on flowers, which is how they've acquired some charge here. They both get the same charge, and it's both positive. So, of course, they're going to repel each other. And when they get back to the hive, they're very close. They're only a centimeter apart. We want to approximate. I love when this word is here, approximate. Approximate the magnitude of the repulsive forces. So we get to basically go by powers of 10. So the force between the bees is going to be KQQ over R squared. Approximate. Let's put in powers of 10. What's 9? We got 9 times 10 to the 9th. Well, that's like 10. That's like 10 times 10 to the 9th almost if we're rounding. So that's like 10 to the 10th. Okay? So that's my approximation. I have 10 to the 10th. They both have a charge of plus 23 pico. If you don't know what a pico is, it's a 10 to the minus 12 of something times a 23, which is like a 2.3 times a 10. So I'm getting a 10 out of there. So let's just make it 10 to the minus 11 because we're approximating here. I'm just going to put in powers of 10 for approximations. And they both have that. So they're both at about 10 to the minus 11 coulombs of charge. How far apart are they? A centimeter, that's a 10 to the minus 2. When I square that, it's a 10 to the minus 4. So I'm just going to say that's a 10 to the minus 4. All right, what have I got on top? I've got 10 tens, minus 11, that's minus 1. So that's minus 12 over minus 4, so minus 8. So they feel a force of about 10 to the minus 8 newtons. Okay, that's the force that they feel because of how charged they are. Now, how does this compare to their weight? Well, their weight is F equals mg. So we've got a mass of 0.1 grams, but that's not a kilogram. So a kilogram is a 10 to the minus, or is a 10 to the third of something. So if they're 0.1 grams, that's 0.1 times 10 to the minus 3 kilograms, or they have about 10 to the minus 4 kilograms of mass, and gravity is about 10. So if I multiply that together, they have about 10 to the minus 3 newtons of weight. So the electric force between them is about 5/10 smaller than their weight, or 5/10 through 2, 3, 4, 5 zeros. So it's about 100,000 times smaller than their weight. So they're not going to feel very pushed around. If their wings are strong enough to lift their weight, which obviously they are, then they are 100,000 times stronger than the force needed to push them apart or push them together. So this electric force is not a big deal to the bees. All right. Hopefully this was helpful to you in how to solve Coulomb's law problems.